Hello everyone, and welcome to our discussion on shear turbulence. We are talking about locations where you find shear turbulence. We already talked about surface friction and Kelvin-Helmholtz waves, as well as temperature inversions. Our next location is fronts. And these are, of course, fronts. You know what fronts are. You remember them. Definition. The old definition was they're a boundary between two different air masses. You probably learned that back in your basic meteorology class. We're going to look at a new definition. We're going to call a front a zone. It's a zone of strong stability, strong shear between two dissimilar air masses. So we still have that distinction of air masses, but now we're looking at stability and shear. So the definition says that it's a zone, and we've talked a little bit about this in the past, that there is a zone where temperature changes. Typically it's behind a cold front. In other words, after the leading edge of the cold front goes through, the temperature drops. But with warm fronts, it's out ahead of the warm front, meaning that as the warm front approaches, temperature goes up until the warm front goes through, and then temperature is pretty much constant. So the width of this zone depends upon the strength of the temperature gradient, how strong the front is basically. And typically the frontal width is, or the frontal zone is typically between 50 to 100 miles wide. And this is a three-dimensional representation of the front showing the warm and the cold air. This represents a cold front, and you notice that the slope of the cold front is pretty steep. We say that the slope is 1 to 50, and what that means is that for every 50 nautical miles that you move in back of the front, if you go up 1 mile, you should be able to find the frontal surface aloft above you. So 1 nautical mile is approximately 6,000 feet. So 50 miles behind the front, 50 nautical miles, you should find the front approximately 6,000 feet. Half of that, 25, you should find it about 25 nautical miles, you should find it about 3,000 feet above you, and so on and so forth. Warm fronts are more gradual in their slope. This is a three-dimensional representation of a warm front. Notice how it's sloping over the cold front, cold air. And notice that if you move 200 miles ahead of a warm front, 200 nautical miles, then the front will be 1 nautical mile above you, or about 6,000 feet. That's the slope of a warm front, 1 to 200. So that's a little bit about the three-dimensional nature of fronts down low. Also, we know that fronts have very strong stability. This picture represents a radiosonde going up through a frontal zone where you have cold air on one side, warm on the other. Not saying which way this front goes. It could be a warm front or cold front. Not sure which way it's moving. But regardless, if you sent up a radiosonde or a weather balloon through the front, initially temperature decreases in the cold air. It goes through frontal zone, and in the warm air, of course, the temperature is warmer, so it starts out at a warmer temperature. So if you connect those two lines from the cold air to the warm air, the temperature lines, you'll see that there's a temperature inversion. And a temperature inversion is a zone or an area of strong stability. Temperature inversions have strong stability, so you know that fronts have strong stability. And this is what we see on the actual SKU-T. Here we see a front at low altitudes, approximately 800 millibars. That's where you see that inversion down low. Sometimes it's higher depending upon what part of the front you're sending up your radiosonde through. And then also fronts have strong shear. You probably know this already. After a front goes through, the winds change direction, and typically on surface charts that's how we find fronts. So down low, most of the strong shear is a result of direction. And here's another picture. It shows you an actual front. This is a cold front across Oklahoma, and you can see how the winds shift. Out ahead of it, the winds are out of the south. Behind it, the winds switch around rapidly to the west. And you can also see that in the radiosonde ascent, looking at the winds that are plotted. You can see down low the winds in this case were out of the north, but as you go up through the atmosphere, the winds switch around to the west. Now this is over Amarillo. back in the cold air of the front that we just looked at. Up high, most of the shear is a result of speed, not so much changing direction, but more speed. So as you go up, you should see an increase in wind speed. That's what you see here up at the 300 millibar level, about 30,000 feet. This is for that case over Oklahoma. There was a strong front, and so you see a strong shear. You see lots of wind, and you see a jet maximum right over Arizona and New Mexico, where the winds are moving about 110 knots or so. And as you move up into Colorado, you see the winds drop down to about 40. So there's strong shear. Also, you can see the vertical shear on a sounding from Amarillo. Down low at about 10,000 feet, though at 700 millibar, the winds are only about 25 knots. And by the time you get up to altitude, you can see the winds are cruising along at 100, 110 or so knots. So strong shear in the speed as you go up with height with fronts. So that brings us to the factors that determine the turbulence that you're going to experience with a front. And there are three factors, and these factors actually came from a study done by Northwest Airlines. Their chief meteorologist, Dan Soa, back in the 1960s, conducted a survey or a study of the turbulence associated with fronts, and they found that there are three factors that determine the strength or the strength of the turbulence associated with fronts. And those three factors were how fast the front was moving, in other words, the speed of the front, the temperature gradient across the front, how much the temperature changes, and then finally whether the front was moving over terrain or not. So here's our first factor. They came up with a rule that said that if the temperature gradient across a front was more than 10 degrees Fahrenheit per 50 nautical miles, then aircraft are more than likely going to experience moderate to severe turbulence. So 10 degrees over 50 nautical miles, in other words, take a look at a METAR or look at a station on the warm air side of the front, look at a station on the cold air side of the front, measure the distance, take the temperature, and then figure out the ratio per 50 nautical miles. If it's more than 10 degrees Fahrenheit, then it will be moderate to severe turbulence. Less than 10 degrees, hardly any turbulence at all. The speed of the front, in other words, how fast is the front moving? Look at the position of the front and then look at it an hour later or a few hours later, and you can estimate the velocity or how fast the front is moving. If the front is moving more than 30 knots, then you can expect moderate to severe turbulence associated with the front. Here's a nomogram or a diagram that was developed by Northwest Airlines showing the relationship between shear, or actually wind speed, and also the temperature difference across the front, or the gradient, and then whether you're going to have wind shear and turbulence, or neither shear nor turbulence. And it looks like the cutoff is 10 degrees Fahrenheit per 50 nautical miles. And then whether you're going to get turbulence or not depends upon not only the temperature gradient, but also the speed of the front. The third factor that Northwest Airlines came up with was whether the front was moving over rough terrain. If it was moving over rough terrain, then you more than likely would experience moderate to severe turbulence. So that is a little bit about the theory of fronts and also the factors that determine shear turbulence associated with fronts. In the next video, we're going to talk about flight planning, things that you look for on weather charts, and how to fly turbulence associated with fronts.